This is Lab 3, which covers black holes and orbits. There are two parts to this lab. Part 1, the goal is to calculate the mass of a black hole through the motion of a star. Part 2 is to explore how gravitational forces influence orbital motion by simulating the movement of a starship around a planet and its moon. The purpose of this lab is to demonstrate the effect of Newton's second law on a celestial system. In this lab, the important equations to remember are Newton's second law, which states that the force is equal to the change in momentum divided by change in time. This equation relates the net force to the change in momentum, which can be broken into parallel and perpendicular components to account for changes in speed and direction. The velocity and position update formula allows us to calculate an object's motion over time using the net force, which will allow us to calculate the motion of the starship. And then the universal gravitational force equation, force is equal to negative g times mass 1 minus 2 divided by r squared, describes the attractive force between any two masses, which will allow us to track the motion of a planet. And here are the initial conditions for my code in part 1. In part 1, the system is the black hole and the star, and the surrounding is everything else. The initial conditions in my code that I edited are the star's mass, which is 2 times 10 to the 30th, and the time interval between each data point, and in this case is 1 day in terms of seconds. And here's the code that I used to estimate the mass of the black hole. This calculation loop steps through the star's position and velocity data over time to determine the gravitational influence of a black hole. At each step, it calculates the star's initial and final velocity vector, then finds the change in position and the rate of change in momentum, which represents the net force acting on the star. The force is then separated into parallel and perpendicular components to show how the star's speed and direction changes. Using the net force and the star's distance from the origin, the loop uses the universal gravitational force equation in order to calculate for the mass of the black hole. This value is printed at each iteration, which allows me to find the average over the total iteration. And here's the results of part 1. The mass that I found for the black hole was 1.918 times 10 to the 34. This was found by taking each iteration of the mass of the black hole divided by the total iterations that I calculated. Now we are on to part 2 of the lab. First of all, the system for part 2 are the planet, a moon, and a ship. And the surrounding is everything else. In the code, the initial conditions are the mass of the planet, the moon, and the ship, as well as the total time that the simulation will be run for, which is 700 hours. And the initial speed in the x and y direction that I found that would cause no collision between the ship and the moon and the planet are negative 2.5 times 10 to the 4 in the x direction and 2.5 times 10 to the 4 in the y direction. And here's the code I used to simulate the gravitational interaction between the planet, moon, and spaceship over time. This was done using the Newton's law of universal gravitation and Newton's second law of motion. At each time step, it first calculates the gravitational force on the moon from both the planet and the spaceship, then adds them to find the moon's net force. It then computes the gravitational force on the spaceship due to the planet and the moon to determine the spaceship's net force. Using these forces, the loop updates each object's velocity and position according to the velocity and position update formulas, showing how they move and interact under mutual gravity. And here's the final result of my simulation. A possible error in part 1 is due to the fact that we approximated the total mass, thus the mass of the black hole could be incorrect. And for part 2, we used trial and error to find velocity in the x and y direction, thus the simulation could have slight errors. Now I'll be answering the question of how the net force and its parallel and perpendicular components are different from the rate of change in momentum and its parallel and perpendicular components. The net force is the external cause of a change in motion, while the rate of change in momentum is the resulting effect observed in how an object's motion changes. Although they are equal in magnitude and direction, force comes from external interactions such as gravity, friction, or tension, whereas momentum change reflects how the object responds. The parallel component of both changes the object's speed, and the perpendicular component changes the direction, linking what acts on the object, force, to how it moves, momentum. Now on to the other question regarding part 2. The To predict the motion of the entire system with a black hole, star, planet, and the moon, the computational model would need to include the gravitational interaction between every pair of objects, since each one exerts a force on all the others. However, the black hole's gravity would dominate because of its massive size, having the strongest influence on the star, planet, and the moon. The other interactions, however, would still contribute, but to a lesser extent, refining the accuracy of the system's overall motion.